Luca Rastello from Synopsys is an application engineer. A ZBoo application engineer at Synopsys for the last year. Previously worked for Cadence, Arc, ARM, and Mental Graphics.
Thank you.
Very succinct. Thank you.
Thank you very much. And I'm going to talk today about the increasing debug complexity that we're trying to address with emulation. So we're going to talk about the debug challenges for exascale designs, and then see how ZBoo addresses those challenges in today's design. So, well, traditionally we used to do IP and subsystem designs. What we're faced with today are designs that are larger, both in terms of size, gates, and in terms of cycles that we need to run on these designs. And that's where we get the exascale, because we get we combine both the design size and the run time, the number of cycles that we need to run on these complex designs for all these various domains. And we find that going into exascale debug requires a higher level of abstractions. So normally and traditionally we do a waveform level debug. We find an issue, we find the bug, we go and look at the waveforms. However, while we're not getting rid of waveforms, they don't necessarily scale all that well when we get to our complex SoC and software debug, and especially when we go to a full system level debug. We'll be focusing today mostly on the waveform and system level debug, and see where our solution can help. Going from the millions of cycles and millions of gates, going to the billions of cycles combined with the billions of gates. So in the real world example of an exascale debug challenge, we want to run some user application on our design and see whether our design is robust enough and works well with that. But before we get there, we need to get the system out of reset, boot an OS, run all the system services that go with the OS, and finally we can try and run a user application. And the user application might be where we see the failure. So the OS hangs, and and we have to restart the system. But the root cause for that failure might have happened a long time before. So it might have been any time before, possibly during the OS boot. Now, traditionally, when you do waveform-based debug, you get maybe a couple of million samples. And to be honest, if you want to go and look at a few billion cycles of waveforms on a billion gate design, well, good luck with that. You're going to be spending probably the rest of your life. Never mind when your project manager comes along and says, is it ready? When is it going to be out? So obviously we need to do something about this, because iterative waveform level debug takes too long, and and it doesn't really scale. If we draw a parallel with graph theory, you can think of iterative waveform level debug like similar to depth first search. If your design is fairly small, maybe you can still manage it. But you often have to go and repeat the search a number of times before you find the bug. When your design grows or your runtime grows, the number of iterations become too large to handle. And we all know that we need to get to the root cause of the problem quickly, because the design needs to go out. Otherwise, our competitors will beat us to market, and then it will be too late. Another problem we have to do is non-determinism. Now, we all want to use high throughput emulation, where we don't have to stop the test bench, the dots every time it has to interact with the test bench. But we want to keep everything running and get as many cycles out of our device under test in the shortest possible time. However, with if you do your typical emulation, you've got multiple test bench interfaces, external peripherals, DDR memory. They're not always deterministic. And when you find a failure during regression, then you give it to your verification engineers to debug the failure, and they run it and say, "Oh, there's no failure. I can't reproduce it." Close the bug because it's non-reproducible, and and then it will crop up again sometime in silicon, and your customers won't be happy. Even if you run it multiple times, it might be really hard to reproduce the same failure. So deterministic failure reproduction is a debug requirement that is essential to maintain. And the last main challenge that we face is that you still have to go back to waveform level at some point. And while for small designs this is not usually a problem, your database and you look it up in your waveform viewer. For large designs, this can become a bit of an issue when you have really large databases and it takes forever to load up in the waveform viewer, and then only to find out that you actually need to go and look at a different bit of the waveform and you go run the loop again. So waveform expansion and load time need to be short in order to do efficient debug on these large designs. So the challenge is that the challenges that come from these requirements are we need higher level analysis, ability to reproduce the failure deterministically, and quick waveform loading and viewing. How does ZeBu help with all this? ZeBu is our platform, is emulation platform, and we can offer high-level analysis of an entire design over billions of cycles of run by using abstract logs like monitors, checkers on all the key interfaces. We can dump key signals at speed. We support language features like assertions, DPIs, etc. And we can do all of this while the emulation clock keeps running. And the system-level data analysis helps us identify the window of failure, basically zoom in on the window of failure that we need to analyze, and it's fairly quick to go around the loop at this level until we find the part of the design where we need to focus in and possibly dump the full waveforms. Deterministic error reproduction in ZeBu as well is a feature that we offer with record and replay. We can effectively record all your test bench stimuli. So where the test benches might not be having a deterministic behavior, because we recorded the signal level stimuli, we can then replay that and rerun the same tests in the same cycle level accurate way and reproduce the same failure that you might have found in regression. We can also do a save and restore, and for the DUT we can save the states at set intervals, so we don't need to necessarily restart your run from time 0 and do your full billion cycle run, but we can restart it at the closest time before the failure or the window of interest. And so you can run your application with your stimuli being recorded. You can save the dots at set intervals during the run, and then you can restore the dot status at the closest time that you're interested in and deterministically reproduce the failure that was reported in regression. And then the last challenge that we mentioned is the waveform loading. We can effectively offer a fast expansion and load of the ZeBu raw data with our waveform visualizer Verdi, and effectively we can split up the the waveform expansion on the machine with multiple processes running in parallel, and give you a very fast time to load large number of waveforms. So Zebu, putting all this together in a flow, we run billions of cycles at workloads at megahertz speeds, so giving you a good value for your money by giving you a large number of cycles that you can run on your complex design. We can stream system level data, record the stimuli and save the DUT state. Then you can quickly go analyze the system level data without having to trudge through gazillions of waveforms to identify your failure window. And you can then deterministically rerun that shorter window of failure to dump your millions of cycles of debug data, and so that you can have the fine-grained waveform debug that you need to do to find the root cause of your bug. And this is enabled by the high-performance waveform expansion debug on Verdi that allows you to analyze the waveforms and the root cause of your issue. And I hope I've kept within my time slots. Have we got time for questions?
Yeah, we have got time. Yeah? Yes, we have got time for questions. Are there any questions? There's one question online which we can take, but we can take a question from the audience first. Okay, so the question online is, does this work with in-circuit emulation? So if you've got external devices, can you do all this store and replay with external devices?
Yeah, I believe so, because effectively the stimuli is recorded at the boundary, and that should still work even within circuit emulation.
Okay. No more questions online? No more questions in the audience? So thank you very much.
Okay, thank you.